Stripping down science. The Naked Scientists.
Hello and welcome to this week's edition of The Naked Scientists with me, Chris Smith, and with Helen Scales.
Hi, Chris.
Researchers this week have discovered the largest ever bird skull. It's nearly a metre long and it belonged to a meat-eating bird nearly 3 metres tall. Find out about that fearsome beast in just a few minutes. I've been down to Buckingham Palace to visit the Queen this week. Christopher, where have you been? Why to the palace to visit the Queen, they say? I'll be bringing you a report that I recorded live there on location, and also how whales have gone into the Guinness Book of Records this week as officially the world's deepest divers.
And also this week we're finding out about the science of the supercool. How low can you go? As well as finding out what superconductors are and how they work, we'll be discovering how superconductors can help us peer deeper into space than ever before, how they can help us watch individual nerve cells working in the brain, and how researchers can now trace the flow of electricity around the heart of a baby developing inside its mother.
And if you're in the mood to win something tonight, we've got a fabulous electronics kit to give away. Now, it doesn't do anything superconductivity, I'm afraid, but it is a hell of a lot of fun, I promise you. All you have to do to win is to answer this simple teaser. What chemical element is a diamond made of?
The Naked Scientists podcast, powered by UK Fast, the UK's best hosting provider, on the web at ukfast.net.
Now, it was a very exciting week for me because I got invited to Buckingham Palace, probably the only time I ever will, to go down and meet the Queen and some of the other royal family. It was part of a special science day which was being hosted at the palace to show young people how exciting science can be, and also why British scientists are amongst the world's best. We've got some of them here in the studio this evening. You'll be meeting them shortly. Now, during the day at Buckingham Palace, 500 pupils from schools and colleges right across the country came to see firsthand a great fun science show called Punk Science, and then to have a chat with some of the UK's top scientists about the jobs that they do. And then in the evening, the Queen, together with Prince Philip and some of the other members of the royal family, had a very special reception in the Buckingham Palace ballroom for some of the country's scientists to get together, mingle, have a chat, and above all, to enjoy some really fantastic champagne. I do compliment the Queen on her choice of Bollinger. Now, one of the first people I chatted to was Rothamsted Research's Professor John Pickett, and he's been working on the problem of why some people taste just too good, or at least if you're a mosquito, that is, because he and his team have found that those of us who are ignored by mosquitoes produce a certain cocktail of chemicals in our skin which keep biting insects at bay. And now he's tracked down exactly what those chemicals are.
I suppose many people will know that mosquitoes show a sort of preference for some individuals and not others. And what we've really done is investigated why that is. And what we found is that people who aren't attractive to mosquitoes produce extra chemicals. And these
this makes them smell bad?
To the mosquito, yes, exactly right. Not to us, but to the mosquito.
So the key question is, can you bottle that and then turn it into the most effective mosquito repellent known to man?
Well, we've bottled it in the sense that we've identified the chemicals mainly responsible. We're now checking out whether we can really use them in some way that would be beneficial.
How did you actually home in on them in the first place?
Well, we surveyed a number of people to find those that were very attractive and those that were unattractive. And then we took the volatile chemicals from those people and analysed them using chemical analysis, but also the antennae of the insects themselves. And that's how we pinpointed the chemicals that were produced extra by the repellent people, and those are the chemicals that we found to be repellents themselves.
When you say you use the insect's antenna itself, how did you do that?
Well, we stick very, very fine microelectrodes into the antennae of the insect, and so we can kind of listen in to what the insect is smelling.
And then once you've worked out what the compounds are that produce the most profound effects, then you know those must be the important ones in the attraction-repulsion.
That's right, and we've been testing those. This work is collaborative with the University of Aberdeen up in Scotland against the Scottish biting midge, and we've got very nice field results there. We've done some lab work on the yellow fever mosquito. That works very well, and we're just about to go out to Africa to work with colleagues there on the malaria mosquito.
So the same compounds work not just in one insect,
but in many. We're hoping that since they work very well against the Scottish biting midge and the yellow fever mosquito, that they will work for a whole range of biting insects.
And the question everyone wants me to ask is, when are you going to have this stuff on the shelf?
Well, we've got funding for 2 years, really, to develop a business plan and to work out how we're going to do this. But the proviso is that we make sure it's available for people travelling to Scotland.
Absolutely. As someone who's been to Scotland and fallen victim to those things, I can wholeheartedly endorse Rothamsted Research's John Pickett, who's trying to bottle the mosquito-repelling odour de human. Now, John mentioned one thing Scotland's famous for just now, those midges, but the University of St Andrews is a world leader in research into marine mammals like seals and whales, and Professor Ian Boyd and his team have developed special satellite tags which can be attached to the animals and then used to find out where they go, how deep they dive, and also where they go to get lunch.
We're trying to understand how these animals operate beneath the surface of the oceans. Until very recently, it was really impossible to observe them, and now with new instrumentation, we're able to gather a lot of information about how these animals live in that deep, dark, high-pressure world.
How are you doing it?
It's mainly using modern instrumentation. We have two basic types, which we're calling satellite tags, which have these antennas on them, and the antenna, when the animal comes to the surface, it sends a message to a satellite which contains the data about the previous dive the animal has made. There's another one, which is over here, which is in the form of a salinity sensor, and that's able to provide us with information about the temperature and salinity in the water column, so we can do the same as the oceanographers do, but without having to take a ship to sea.
This thing's about the size of a computer mouse, so you just, glue that on the animal's head or something?
It goes on the back of the head, and it goes on the fur, and then when the animal molts, it molts once a year, the device falls off, so the animal's not permanently marked with the device. We have another version here which actually dispenses with the satellite link and uses a mobile phone, so whenever it comes into mobile phone range, it sends the information through the mobile phone network to us. And the development of this tag will probably involve animals being able to phone each other as well, so that's interesting.
Why would they want to do that?
Well, the mobile phone network only goes out to sea for a very short distance. So what we want to do is allow animals to collect the information about all the other animals there are around if they come in contact with them, so that we only need to actually see one animal to get the information about the whole network back from them.
It's Professor Ian Boyd from St Andrews, who's got seals talking, quite literally. Now, if you didn't think that was sufficiently out of this world, one of the most incredible things to grace the Buckingham Palace ballroom, apart from a massive model of Einstein's head that let you cycle through his brain, was a very large screen providing a three-dimensional view of the surface of planet Mars. It played just like a movie, and it looked quite literally as though you were flying across the surface of the planet in an aeroplane, buzzing past craters and impact canyons and various other erosion features. And it's been produced using stereo photographs taken by the Mars Express satellite, which is currently orbiting Mars, and capturing the images as it goes. And one of the scientists on that project is the Open University's John Murray.
These are images from the Mars Express spacecraft, which is the first European spacecraft to another planet. It's also the first stereo camera ever being flown to another planet, which is quite amazing. So what you're seeing here is a model of the surface created from these stereo images, and we're flying over the surface, skimming above the mountaintops and so forth.
So this is almost as though you were literally taking a bird's eye view of the surface of Mars?
Exactly, yes. These are taken from a spacecraft which is orbiting Mars at the present moment, so it's sending back pictures all the time. So from these we can create models where you can go right down to the surface and explore and measure heights, measure angles of dip of strata, do geological field work in virtual reality.
Is the orbit such that you'll be able to get a complete comprehensive map of the surface of Mars then eventually?
Well, provided we get funded, yes. I mean, we've just had the mission extended for another 2 years, so we should be able to do it. We hope to have 100% of the planet covered between a resolution of 10 metres and about 30 metres, so something the size of this room would be easily visible in those pictures. So that means that we would actually know the surface of Mars better than we know the surface of the Earth, amazingly.
Certainly is amazing. That was the Open University's John Murray talking to me at what I think probably counts, and you can shoot me down if I'm wrong, but I think that's the first official podcast from Buckingham Palace.
Fantastic. And did you actually get to meet the Queen?
I did raise a glass of excellent Bollinger to Her Majesty, and I did have quite a nice chat to Prince Philip, who was more intrigued than anything to know why I wanted to call myself the Naked Scientist.
I do, indeed. And did he want you to demonstrate this?
No, not in the flesh, no. But he was intrigued, and he said, hasn't that blinking chef got there first? And I said, well, that is a slight impediment, but actually the reason we do it is because it's all about stripping down science and laying the facts bare, but more than anything, it's because then people do exactly as you did, Your Royal Highness, and come and ask me why I do that.
Fantastic. I think it's great. And I could certainly do with a few glasses of champagne on the Queen, so next time perhaps I'll go along too. Anyway, Chris, I have a question for you. Enough of all this hobnobbing with famous people. How deep do you think a human has ever dived under the sea without a scuba tank, just holding their breath?
So what, Guinness Book of Records?
Yeah, or just how deep do you think we can go? Any guess?
I would say, 300 metres?
That's a bit much, actually. We've only managed to get to about 200 metres. The current...
That's still a long way, though,
It is
isn't
a very long way. It's an unofficial world record at the moment, but held by an Italian chap called Patrick Massimo. And I just found on YouTube the other day, apparently a video of him making this dive. And I don't know if it's really what it says it is, but it's quite interesting to have a look at. But anyway, this is nothing compared to the far superior diving mammal, which has recently been announced as the new world record-breaking deep diver. The Cuvier's beaked whale has now been recorded as diving down to nearly 2,000 metres, around 6,230 feet, or well over a mile.
Why do they need to go that deep, Helen? What are they actually after?
They're feeding down there. I don't think we can answer the question why they need to go quite so deep. It could certainly be something to do with the abundance of different species. They feed on things like giant squid, which are also very deep species, so it could be something to do with that, but we don't quite know that yet, and quite why they should go to such extreme depths. But and this is all according to a study published by an international team of scientists led by Dr. Peter Tyack at the Woods Hole Oceanographic Institution in the United States. Now, they used possibly less high-tech tagging than we've been hearing about earlier from your time at Buckingham Palace. These are actually digital archive tags, or D tags, that were developed at Woods Hole, and they don't have any satellite or mobile phone technology. We don't get them phoning home their information. They actually just last on the whale for about a day. The researchers stick them on with suction cups onto the top of the whale when they reach the surface, and then after about a day they drop off and float back up to the surface, and with a radio signal you can go and find where they've dropped off. So there's not quite such high-tech kind of long-term information. But what they have done is basically follow 10 beaked whales and seen how deep they go. And they have found these record-breaking depths. And it's not just the one depth that it's reached. It's more the fact that these beaked whales seem to, on average, spend much more time at much greater depths than other animals that we know a bit better. We know more about things like sperm whales and elephant seals, but they don't spend so much time so deep down. And as we say, it's something to do with feeding and cutting down there to these animals. And one of the really mysterious things the team found in this study was that the whales come up to the surface from these very deep dives very slowly compared to from the shallow dives. Now, this
is to stop them getting the bends, though, isn't it?
Well, that's what you think. See, it's what human scuba divers would do to avoid getting decompression sickness or the bends, which is basically when nitrogen gas that's dissolved in your blood under great pressure comes bubbling out. It's a bit like opening a can of fizzy drink. But for the whales, it shouldn't make any difference how quickly they come up once they've reached about 100 metres, because when they get to that point, their lungs essentially have collapsed, and there's no gas left in them to dissolve into the blood, and so they're really at no extra risk of getting the bends. So this is a bit of a mystery. We don't quite know why it is they come up slowly, but it does point to one slightly unfortunate aspect of these whales, is that they have been found on mass strandings on beaches associated with military sonar when there's a lot of noise going underwater, and they've been found to have symptoms of decompression sickness. And we think that even though these whales dive so deep, and so they are adapted to very extreme depths, this isn't actually anything to do with making them more susceptible to this underwater sonar. But maybe the sonar is making them make more shallow dives to about 50 metres, where they are at more risk of getting the bends.
It's Chris and Helen, and this is The Naked Scientists. If you'd like to join in and ask us any questions, our phone lines are open 08459 25 2000, or you can email chris@nakedscientist.com or text in on 07786 20 1960.
Yep, we've already got some people who are along the right lines. Keep your calls coming in, but Keith in Peterborough, you're doing very well there. Andrew in Cambridge and Norman in Hunstanton, thank you all for your calls, but do keep calling if you think you might know the answer to our question.
Which is, what chemical element is a diamond made from? We've got a fabulous electronics kit, which has been donated by Noisemakers, which are a group of scientists that like to make a noise about science. More on them on the web at noisemakers.org.uk. Now, here's a bird you definitely wouldn't want to peck on the lips from, Helen. Not you personally, I mean, anyone really. It's because US fossil hunters have come across the largest bird skull that's ever been found. This massive beast had a beak that was at least 75 centimetres from the back of its head to the tip of its beak, so it was huge. It would have stood about 3 metres tall. It didn't fly, but it could run very, very fast. These fearsome animals were meat eaters. They looked a bit like a giant secretary bird. They have sort of crane-like legs and an eagle's body. And they came from Argentina and Patagonia. They first evolved about 65 million years ago, about the time when the dinosaurs were disappearing. And they persisted only until about 2 million years ago, so until relatively recently. And the thing is that they weren't competing against any other major carnivores, because they were the top dog, quite literally, and so that enabled them to get very, very large, and as a result, they were the thing that would have been chasing you if you took a stroll around South America up to about 2 million years ago. It's been discovered by a guy called Louis Chiappe, who's at the Los Angeles Natural History Museum.
That sounds absolutely terrifying. And while we're talking about birds, I've got an email here from Leslie Knowles, who says that she cracked open a large chicken egg this morning when she sent the email, and out came the egg white, and the yolk, and another fully formed shelled egg, about the size of a pullet
Inside
egg.
the first egg?
Inside the first egg. So a bit like a Russian doll. Any thoughts on why this happens? We've been raising eggs, she says, on her farm for a long time, and this is the first one.
I've never heard of that happen. The reason that sounds a bit bizarre is that, of course, when an egg forms, the chicken makes the egg and then puts the shell around it as it descends along the ovipositor, the oviduct in the chicken. So for that to have happened suggests that an egg formed or misformed and then got kind of engulfed by another egg that was forming once it had already partially formed. And it's a bit like people who, I mean, there have been cases of ladies who've given birth to babies and they've found the remains of a dead twin inside one of the surviving babies.
There are lots of strange things that can go on, aren't there?
There certainly are.
The Naked Scientists, supported by the Wellcome Trust.
You're listening to The Naked Scientists, and we are getting floods of phone calls for our teaser question at the moment. So anyone else there who has any idea what diamonds are made out of, do keep your answers coming in. We've just heard from Mike in Malden and Henry in Wistow, and they are both along the right lines. Thank you for your calls.
We want to know, what is a diamond made of? What chemical element would you find in a diamond? If you think you know the answer, 08459 25 2000, email chris@nakedscientist.com or text in 07786 20 1960. Got an email here from Tim Hart, who says, hello, I'd like to say I love your podcast, by the way. I listen to as I am working patching precast concrete buildings. I've come across a website for a gas made using water that ignites, but it's not hydrogen. I'm just wondering what your take is on this. Any ideas?
Sorry, say
So he's come across a gas made with water that ignites, but it's not hydrogen.
And well, the gas you get out of your cooker?
No, I think it's acetylene. Because if you think of people who go potholing and miners' lamps, they use acetylene, don't they? And that is made by using calcium carbide. And calcium carbide is calcium with a couple of carbons stuck onto it. And when you drip water onto it, and you used to be able to get bicycle lamps that work the same way, you had this sort of big biscuit of calcium carbide you put in the bottom of the lamp, and then you had a tiny dripper from a tank of water above, and it would drip water on, and when the water hits the calcium carbide, it reacts to make acetylene, 2 carbon atoms stuck to 2 hydrogen atoms, which of course is in acetylene torches, and it burns very brightly, beautiful, and it also makes some lime for your trouble. So I think that's probably what he's talking about.
Excellent. I've got an email here from Kai in China. Thank you ever so much for writing to us, because it's the first time apparently she's ever done that from listening to a show. She says she enjoys it very much, and she's learnt lots of different things, which is excellent, and she has a question for us. She has thought about it many times, but how is it that some people can memorise more things than other people? I think this is a perfect question for Chris, who I think must have a what do you call it, a photographic memory. I can't even remember the word myself. A photographic memory, indeed. Is it because you've got difference in our brains? Is it different sizes of the brain? Can we tell the difference between people with big brains and normal people, she says, which I think is quite nice. But basically, why do some people remember more things than other people? Any ideas, Chris?
Well, I think language is a good index here because, of course, to know a language, you have to know thousands of words. The average person who speaks English well probably knows 20 to 30,000 words. Shakespeare probably knew 40,000 words. And there was a study done recently by researchers at University College London. I think the lady's name was Andrea Michelli. Or Michelli, I think she might be Italian. What they did was to look at people who were bilingual, and they used a brain scanner to look at the thickness of the rind, the cortex, the layer around the outside of the brain, and measure it in people that were monolingual, spoke one language, and compare it with people that spoke more than one language. And what she found were these obvious structural differences. The people that were bilingual had a thicker language area in the brain. So the evidence is that if you can remember more things, you train your brain and it develops more connections, and it's those connections that probably underpin the ability to store more information and recall more information.
So it's not a pre-adaptation, it's that you can train yourself and your brain will change as you learn more words.
Sorting out the sparks from the quarks. The Naked Scientists.
Now, I did say we're going to do a superconductivity show on the super cold this evening, and what better than a superconductivity kitchen science to go with it? This week, Derek is with Professor Ted Forgan from the University of Birmingham, and he's got student helpers Kathy and Dan from Hills Road Sixth Form College in Cambridge, and they're going to be looking at the science of the very cold. Now, although you can't do this experiment this week at home, you can do a bit of armchair science, a bit like Einstein, so we want you to see if you can predict what the outcome's going to be. Derek, what do we have to do?
Hello there, welcome to Hills Road Sixth Form College, where we've come this week to do some fantastic science experiments which you can hopefully predict the outcome of at home. We haven't got one which you can really do at home, but believe me, this is really interesting, and we want you to try and tell us what you think is going to happen. So with us is a bit of a new recruit to the Naked Scientist who's going to be running this experiment, so would you care to introduce yourself for us?
Hi, I'm Ted. I'm a professor of physics at the University of Birmingham.
Thank you very much for coming down. And we've also got two volunteers who've come in to help us do the experiment as well. So could you just tell us your names, please?
Kathy Raven.
I'm Dan.
OK, you guys are in year 12. Can I just quickly ask you guys, you must be scientists, I'm sure. That's why you've come down. But what do you like about science, Kathy?
It's really interesting. It's kind of about how the world works.
OK, and I think we'll be discovering about how some stuff in the world works today. And yourself, Dan?
I'm not sure. I'm just good at it.
Oh, OK, so he says. So he says, and we'll find out. Ted, you've got to test whether Dan's good at it. OK, basically then, we have a little setup that Ted has prepared for us. We have a plastic tray, which is quite a small tray, but it's basically the sort of thing that you might serve your dinner up on. We've got an aluminium frying pan as well, and we've got a rather strong magnet, which has come from the lab that Ted works in University of Birmingham. So, Ted, what we're going to be doing with all this stuff, perhaps you can instruct Kathy and Dan.
OK, well, we've got this strong magnet, and I want you to slide it down first the plastic tray, and then slide it down the thick-bottomed, rather nice, shiny aluminium frying pan.
OK, who'd like to try the tray? Kathy, if you just come forward. OK, now what we want you to do is just put the plastic tray at a bit of an angle, so it's kind of almost vertical but not quite, and then slide the magnet down it and say what happens. OK, so what happened?
It's just gone straight down.
OK, so it just slid down due to gravity pulling it downwards, I suppose. That was fine. OK, then, now, next, Dan, what we want you to do is we've put the frying pan, the back of the frying pan, at the same angle, so it's almost vertical but not quite, and we want you to slide it down, again, this magnet, and tell us what happens.
OK. It goes down, very slowly.
And how many seconds do you think it takes to go down?
About 4 or 5. Maybe a bit longer.
OK, then, any idea why that's happening? Why is it much slower sliding down the pan than the plastic?
I'm guessing it's because of the metal, how the metal and the magnet just work together, so it attracts.
All right, then. OK, well, Ted, we've seen this magnet go slower down the aluminium frying pan than it does down the plastic tray. But I suppose the question we firstly want to ask is what's going on with moving magnets and currents and electricity and so on. So please explain for us what's going on here.
So the big difference between the aluminium and the plastic is the aluminium is a metal and can carry a current, and the plastic carries no current at all because it's an insulator. And the thing that's going on here, when you move a magnet past any metal, it'll start a current flowing around it. This is a very important thing for generating electricity because all electrical generation happens by moving magnets, moving past coils, making voltages and currents, which of course we use in our home. In the aluminium, of course, we're not doing anything useful like that, but nonetheless, the moving magnet is making the currents flow in the aluminium. OK, then. So what we do when we slide that magnet down the aluminium frying pan is that we're moving a magnet past a metal, and so it makes an electrical current. Of course, does that current actually stay there? Is it maintained? So the currents are actually trying to hold the magnet up. And if they kept on flowing, then the magnet would stay suspended over the aluminium, but it is slowly falling. That's because the currents are dying away and allowing the magnet to fall. OK, then. So what we've got then is we've got a magnet sliding down an aluminium frying pan surface, and because that generates some current, the aluminium can carry some electrical current, it tries to hold the magnet up a bit and slows it down as it slides down. The plastic tray, of course, as Ted said, it's an insulator, doesn't carry any electrical current, and so the magnet can't generate any current in it. That can't stop it from sliding down, and so it slides down very, very quickly. Now then, what we're going to do now is actually do something else to this frying pan and wonder to ourselves what is going to happen. So what are we actually going to do, Ted? We're going to cool it down much colder than room temperature and then see whether the magnet falls faster or slower. Perhaps you'd like to guess. OK, then. Well, of course, we have Kathy and Dan here who are very willing to guess, I'm sure. So, Dan, what do you think is going to happen when we cool that frying pan down and then slide the magnet down it?
I think it's going to go faster because there's not going to be as much of a current because it will have less energy, but I'm not sure.
All right, then you say faster. Kathy, what about you?
Yeah, faster as well. I think maybe the coldness will make so that the atoms are more held together, so there's not free electrons to move about.
OK, right. What we're going to do is we're going to find out. And also, we'd like you at home to have a guess, if you like. So you can ring us, The Naked Scientist, and tell us what you think. The number to call is 08459 25 2000. And you can also email chris@thenakedscientist.com. So anyway, we'll be coming back here to Hills Road Sixth Form College with Ted of Birmingham University and also Kathy and Dan to find out what happens. So it's back to you in the studio till then.
Thank you, Derek. What do you think at home is going to happen? Will the magnet fall down the freezing cold frying pan faster? Try saying that when you've had a few of those Bollingers at Buckingham Palace. Or will it go slower than the frying pan at room temperature? You might as well have a guess, because up for grabs this week is a fantastic electronics kit with 30 different experiments on it. No superconductivity, I'm afraid, because you need some liquid nitrogen for that. But it's been donated by the kind people at Noisemakers. They're a group of scientists with a passion for communicating science and making noise about it. You can find out a bit more about them on the web at noisemakers.org.uk. Helen.
And don't forget, we're also asking you our teaser question for today, which is, what chemical element is diamond made out of? So, yes, do call us on 08459 25 2000, just to remind you of that number, 08459 25 2000. Send us a text message on 07786 20 19 60, or email chris@nakedscientist.com. And we're actually getting a bumper crop of your calls today, so thank you to everyone who's called in. Lots of right answers. We will definitely have a large hat to put you all in. But just thanks especially to all of you, Wendy in Northampton, Aileen in Thorney Cole, Shirley in Fakenham, and Pat in Framington. Framingham, you're all along the right lines. Thanks for your calls.
Bob in Halstead rang in and said, on the subject of superconductors, he's not had any on a bus lately. But anyway, let's have a quick chat to Jean, who's in Cambridge. Hello, Jean.
Hello.
What do you want to talk about?
I want to talk about fruit in a bowl that's rotting down, and you get horrible little black flies come out of them.
Uh-huh.
How does it get there?
Well, those flies are what are called Drosophila. They're fruit flies. They're the favourite friend of geneticists because they're very easy to do experiments on. And if you were listening earlier to what John Pickett, the guy from Rothamsted Research, was saying about mosquitoes, he was describing how chemicals come off of the target of different animals, and those animals use very sensitive antennae to track down the source of those particular chemicals. So in the case of a mosquito, for example, it's sniffing out various chemicals coming off of your skin, and the mosquito follows a chemical gradient. So it follows its nose, a bit like the kids on the Bisto advert, going towards the source of the smell. So Drosophila, little flies, they're in the environment pretty much all the time. They lay eggs, and when those eggs hatch, the flies come out, and in the warm environment of your house where there's lots of things for them to eat, and they like eating fruit because they go to fruit that's a bit mouldy and they can stick their mouth parts into it and suck up the sugary solution, they just come out and then home in on your fruit bowl. The other thing that attracts them is red wine. They like red wine and also white wine because the volatile agents, the alcohols, smell a bit like fruit because, of course, wine comes from fruit.
Oh, right.
Quick go at the quiz.
OK.
Gut specialists at the University of Bristol have produced a stool form scale for assessing the consistency of faeces, or number twos, to give them their other name.
Right.
Fact or... Do you think that's fact or fiction?
Fact.
I'm ashamed to say you're absolutely right. They have indeed produced a chart ranging from 1 to 7. Number 1 are small lumps like rabbit poos, through to number 2. And apparently number 4 is the most comfortable one. I'm going to stop it there. That's too much.
Yes, they describe it as like a sausage or snake, which is smooth and soft. The average person has about 300 hairs per square centimetre of headspace. Do you think that that is fact or fiction?
Fiction.
No, I'm afraid actually that one's true. We have between 100,000 and 150,000 hairs on our heads before we go bald, which is an average of 300 per square centimetre.
OK.
1 out of 2, Jean. You're in the lead at the moment. Thank you for joining us on The Naked Scientist.
Thank you.
If you'd like to get a call in, 08459 25 2000, email chris@nakedscientist.com, or you can text in on 07786 20 1960. Had a text from Eddie, who's in St Lawrence Bay, and he says, why does the moon look larger on the horizon? The reason for that is it's an optical illusion, Eddie, because the brain has no frame of reference when the moon is high up in the sky, whereas when it's on the horizon, the brain is comparing the size of the moon to other things in the same frame of reference. There are trees, there are buildings, there might even be people as well as the moon, and therefore the brain fools you into thinking that actually it's a lot bigger than it really is. Helen.
I've got an email here from David, who said, in our programme about cat allergies, we mentioned the cause was the saliva from their skin. He'd like us to clarify, did we mean that it was saliva when a person is licked by the cat, or by petting their coats after they've licked themselves, or a secretion from their skin with no physical touching needed? What's that about, Chris?
OK, the situation here is that these cats that people are allergic to, people are reacting to a substance made by a gene called FEL-D1, fel for feline D1. It's produced in cat saliva, so when the cat grooms itself, it licks its paws and then grooms itself with the wet paw. The FEL-D1 gene product, this protein in the saliva, then goes onto the fur, and then when the cat sheds that protein from its fur, it goes into your nose and makes people sneeze. And there's a company over in California, in America, and they've bred a type of cat which doesn't have that particular type of that gene. It has a slight variant of it, and they say, it hasn't been proven scientifically yet, but they say that it's actually non-allergenic, and they're charging $4,000 to breed you one of their cats.
Sounds like a good thing to get breeding a cat. I was rather shocked when I saw they'd bred a cat with tiny stumpy legs so it didn't climb up on your furniture and scratch it. It just looked ridiculous.
It is The Naked Scientist, Chris and Helen, and we're talking this evening about the science of superconductivity. And here in the studio with us is Tim Jackson, who is from the Emerging Device Technology Department at Birmingham University. Hi, Tim.
Hello, Chris.
How are you?
OK, thank you.
Thank you for coming to join us. We've talked up superconductivity quite a lot. People have been hearing us doing some experiments there, but maybe you should just sort of backpedal a little bit and tell us, what actually is a superconductor?
Well, superconductors, some people call them the superheroes of material science. They're very surprising materials. You cool them down through some special temperature called the transition temperature, and at that point they lose all of their electrical resistance. And electrical engineers can employ this quite surprising property in a variety of different situations.
Well, why do they lose all that resistance? I mean, what is resistance for a start?
Well, we have to go back a little bit and think about electric current going through the wires, say the copper wires in your house. The electrons are more or less free to do what they want as they do that, as they're pushed by the voltage through the wires. But they do encounter some resistance, and that resistance is actually that they collide with the atoms in the material. They lose a bit of energy when they do that, and that energy comes out as heat. In fact, that's why a light bulb works. It's really the resistance of the filament makes the bulb hot, and so it glows white. Now, in a superconductor, at room temperature, the electrons again are doing their own thing. They're not taking much notice of one another. You now cool it down, and you really have to cool, perhaps to minus 180 degrees centigrade. And as you get close to that, the electrons start to take a bit more notice of one another. You can think that they start to flirt with each other a little bit. You go down through that transition temperature, and they hold hands. And those electrons, once they're holding hands like that, they can't be knocked off course, and so they move through without any problems.
And I suppose the goal of this is that 180 degrees below zero is not a practical temperature to work at. If we could make this happen at closer to room temperature, it'd be ideal.
Well, you'd be surprised, to be honest. Minus 180 degrees centigrade is the temperature of liquid nitrogen. Nitrogen makes up 80% of the air that we breathe. And as far as technology goes, it's not so hard to cool down to those sorts of temperatures. Now, 20 years ago, there was a class of superconductors discovered which we call high-temperature superconductors. And high and low are all relative in this context. If you can cool down and make things superconductor at liquid nitrogen temperatures, there's an easy technology there. Between 1911 and 1987, most superconductors that were known, you had to cool down to within a few degrees of absolute zero, which is minus 273 degrees centigrade. And that was a barrier to most applications.
So how do you actually make something superconduct? How do you decide this is the recipe I need to get together to make a chemical combination that will have these properties?
Well, that's a very good question. There was a theory that was developed in the 1950s about how these very low temperature superconductors worked, and most people thought that means you can't make a superconductor that works above perhaps 25 degrees above absolute zero. But people following the guidelines of those theories were looking at other materials, and in particular oxide materials. And these are materials that are a little bit like ceramics. There's 3 metallic elements and oxygen in a compound in there. And what they found 20 years ago was that these would superconduct at much higher temperatures. And it is now still a big challenge for theoretical physicists to work out exactly how that takes place.
Now, what sorts of applications might there be if we are able to crack this nut and make these materials in the way that we want? What will we be able to do with them? And how are they being employed at the moment?
Well, there are applications now. As I say, cooling down liquid nitrogen temperatures isn't so very difficult. And one of the applications that our research team are working on in Birmingham is making filters for radio astronomers up at Jodrell Banks radio telescopes.
And when you say filters, what will that do? How does that work?
A filter is the electrical equivalent of a bouncer in a nightclub. A bouncer in a nightclub with a selective door policy has been told certain people come up to the door, you let them through with no interference. If they're the wrong people wearing the wrong kind of clothes, just send them back and don't let them through. Now, a filter is an electrical circuit that does just that. But what the circuit does is it's allowing through particular frequencies, electrical signals that you want. The problem for radio astronomers is there's a lot of electromagnetic pollution. So, for example, you're looking for a distant object in the universe, you want to study its properties. But all the satellite communication systems we have, all our mobile phones, all our televisions, are polluting the frequency space. That means the astronomers have to spend a great deal of time on their telescopes averaging out the data. If you can find a way to help them use their telescope more efficiently, they can do more experiments. And our superconducting filters do just that, because they cut out that noise.
Why do you need a superconductor to make that kind of filter, though? Why doesn't just standard electronics do it?
The reason you can't do it with standard electronics is because there's always some loss. As we talked about earlier, in a normal metal, there is always some resistance. And when it comes to making electronic filters, that sort of loss means, for a start, you have to have large devices, but also they will never pass through the signals you want without some attenuation. If you want the signals to come through clean and undiminished, then you need a superconductor.
Now, hasn't Birmingham got another claim to fame in terms of superconductivity in the form of the maglev? Wasn't there is that at Birmingham, where they actually had a train which drifted along on magnets, so it was not actually touching the ground?
That's right. There used to be a train, and it hasn't been running for 10 to 15 years now, which went from the passenger terminal at Birmingham International Airport to the railway station. That was a magnetic levitating train, but it wasn't a superconducting train. And there were some problems with that. People thought it was a bit wobbly and bobbly, and that's perhaps because the technology was much earlier.
So is that the kind of thing that we could look forward to if we are able to get a handle on getting superconductivity working as well as we'd like to? Is that the kind of thing we can look forward to, is better transport?
Well, better transport is one of the large-scale applications that's getting people excited at the moment. There's a test track in Japan at Yamanashi with a train which contains wires made of superconducting material in the floor of the train. And they are cooled down, and they're used to drive a current through those coils, and that repels against some currents in other coils in the track and lifts the train up. The advantage of doing this is there's no rolling resistance, and this train has now been tested at speeds up to 360 miles an hour. It's exciting because this gives you high-speed transport without the need for aeroplanes, which have very high environmental costs, particularly at takeoff and landing.
Fancy listening to The Naked Scientists in your bed, on your way to work, or even at work? Why not subscribe to our podcast? For more information, visit nakedscientist.com/podcast.
It is Chris and Helen, and this is The Naked Scientists. We're talking this week about the science of superconductivity, and from the University of Birmingham's Emerging Device Technology Department is Ed Tart. Hi, Ed.
Hello, Chris.
Thank you for joining us. Now, we've heard from Tim all about the science of superconductivity, and we began to explore some of the applications, but this is an area where you're really pushing the boundaries.
Yes, I mean, probably the most successful application of superconductors is actually some of the medical imaging scanners you were talking about earlier, because the long tube light scanners that people are often experience these days are actually based on superconducting magnets.
Like MRI, magnetic resonance imaging, for example.
Exactly.
Now, why do they need a superconductor?
They need a superconductor because you want to produce a very large magnetic field. What you're trying to do is you're trying to line up all the protons in the water atoms in your body, and to do that, and get a big enough signal-to-noise ratio out of the system in the end, you need a very large magnetic field. Now, you could do that with a magnet based on copper wire, but then the amount of heat that would be generated would be too large for the patient to be inside. You'd have to do a lot of cooling. And so the advantage of having a superconducting magnet is that the superconducting wire is cooled anyway, but you have this much larger current without the patient being exposed to large amounts of heat.
Is it just patients that you can explore using this technology? Are there other things that you can image and where this technology is useful?
Yeah, well, it's been used for a whole range of things. I believe that in various institutions, particularly even in Cambridge, they've looked at the defrosting of courgettes inside an MRI scanner.
And why is that useful?
Because you can look at the inside of the object that you're trying to examine, as well as the outside. So you can see, you can do a section of the structure inside.
While it's frozen? Without having to chop it up and ruin it?
Exactly.
Oh, I see. So you can actually see what would happen if you dumped that thing into the freezer?
Pardon?
So you can actually see what would happen if you did put a courgette into the freezer. You're always worried about what would happen when you actually cut it open. You would obviously spoil whatever was going on inside.
Or what happens when you take it out and let it defrost?
Now, what about actually increasing the resolution of MRI? Because it's all very well, it gives us these wonderful pictures of gross structure of the brain in a way we could never have dreamt of seeing before. But now, there is a way I understand, which is referred to as SQUID, which enables you to look at what the brain's doing almost neuron, nerve cell by nerve cell. Yes.
Well, not quite nerve cell by nerve cell, but certainly with a superconducting quantum interference device, or SQUID, you can image the location of activity inside the brain by detecting the magnetic fields generated by the currents flowing inside the brain.
And what sorts of things or what sorts of questions does that enable you to ask?
Well, one question you can ask is, you can answer is, if you imagine a patient who has a brain tumour and you want to remove a surgeon wants to remove the brain tumour, and you want to work out what the best way into the brain of removing the tumour is without damaging the sense of hearing or touch and so on. And so what you can do is you can put the patient inside what's called a magnetoencephalography scanner and play a tune into the patient's ear, and because this MEG, this magnetoencephalography scanner, has an array of squids around the head, you can map the distribution of magnetic fields associated with that piece of brain activity and work out exactly where in the brain the auditory complex is, so that when the surgeon wants to remove the tumour, they can remove it without creating damage.
What about turning away from the brain and towards other tissues, such as the heart?
Yes, by using an array of squids, you can image the current distribution in the heart and therefore look for short circuit, because when the heart beats, you have the cells generate voltages, but certain conditions generate short circuits between different parts of the heart, and you can see those by using an array of squids.
Ed, thank you very much. That's Ed Tarr from the Emerging Device Technology Department at the University of Birmingham. And if you'd like to ask either him or Tim Jackson, who's here with us this week, any questions, 08459 25 2000. Now, we were asking you this week to have a go at our armchair kitchen science, to have a think about what would happen when that magnet slid down the cold frying pan. We heard from Alec in Peterborough, John in Colchester, Daniel in Sittingbourne, Andrew in Cambridge. But John got there first. He's on the line now. Hi, John.
Hello there.
What do you think happens?
Well, I think it'll slow down or stop altogether.
And why do you think that?
Well, eliminating the resistance of the aluminium, you've got greater currents flowing, therefore there'll be greater retardation of the falling magnet.
Shall we find out if you've got it right?
Hope so.
Stay on the line, John. John's in Colchester, but Derek, meanwhile, back to you at Hills Road to find out if we're right.
Hi there, welcome back to Hills Road Sixth Form College in Cambridge, and I'm here with Ted of Birmingham University and also Kathy and Dan, who've been waiting to see what happens in our experiment. Now, what we've been doing is actually taking a magnet, sliding it down a plastic tray and also an aluminium frying pan, and seeing that it slides much slower down the tilted aluminium frying pan. What we've done now is we've cooled this aluminium frying pan down massively. We've cooled it down to minus 196 degrees centigrade. And how have we done that, Ted?
We poured it full of liquid nitrogen, which boiled away merrily, and now we just poured away the liquid nitrogen, so we've got a very cold, frosty-looking frying pan at this very low temperature.
Yes, that's right. So this frying pan has gone from kind of grey to almost white. It looks freezing, and it's got loads of kind of steam coming off it, so it's very, very cold indeed, liquid nitrogen being just a very, very cold liquid. So, Kathy and Dan, we are now going to slide down the magnet down the aluminium frying pan. Would one of you care to do it? OK, Dan, you're going to do it. OK, then. So be careful not to touch the frying pan, because it's very cold, but tell us what you see when you put it on there and slide it down.
Very slow. So it's going even slower than it was before.
There we go. We can just about hear it. Very, very slow. OK, so Ted, can you explain to us why is it that that's actually gone slower, even slower than it did on the warm aluminium?
OK, so what we've done is we've cooled down the aluminium. The atoms in the aluminium are moving slower, and they're getting less in the way of the electrons that are carrying a current through the aluminium. So it actually has a lower electrical resistance. The currents that the magnet are making are therefore dying away more slowly, and so the magnet falls slowly.
So earlier on we talked about how aluminium can carry a current, and when you move a magnet past the aluminium surface of the frying pan, it generates a current. However, that current didn't stay there, and because it died away, that allowed the magnet to fall down very, very gradually. It was trying to keep it up, but it wasn't managing very, very well. But you're saying then that when it's cold, it actually keeps its current even better. And so it can actually fall slower. It keeps that magnet up better. Is that right? Have I got that the right way around?
Yes, indeed. Yeah.
Hey, okay. I feel massively happy about that. OK, then. So, Kathy and Dan, I mean, we've managed to decrease the electrical resistance. So this pan, now it's cold, conducts electricity even better. But what do you think would happen if we actually managed to get rid of all the resistance? So this thing conducts electricity perfectly. Imagine that. What do you think would happen to the magnet, Kathy?
It would go even slower or just not go at all.
OK, yeah, just stay there. OK, then. So, Ted, I mean, can we actually do that?
We can't do it with the aluminium, I'm afraid, but we can, using our liquid nitrogen, do it with another material called yttrium barium copper oxide, to give its full name, which is a ceramic which goes superconducting at the temperatures of liquid air. OK, now then, this term superconducting, I mean, it sounds very dramatic, but what does that actually mean? It means that if you start a current flowing round it, it never stops. So if the current never stops, the magnet never falls.
OK, so we've talked about things having a bit of electrical resistance, so eventually a current in them does die. A superconductor, therefore, it can't. The current can't die. It will carry on forever. So what, have we actually got one here?
Yep. We've got a little plastic tray here with liquid nitrogen boiling away, and in the middle is this black disc of ceramic. It looks rather like a disc that you might buy, a poorly made piece of pottery. And it's not, however, like pottery, because it actually is not only a metal. It carries a current, and it carries a supercurrent.
It carries a supercurrent perfectly. OK, there we go. So, yes, as you said, we've got this kind of disc. It's about 2 inches across, and it's currently bathed in liquid nitrogen, so it also is very, very cold. And what are you going to do with it, Ted?
So what we're going to do is we're going to take a little magnet, like I ran down the aluminium pan, and I'm going to lower it down towards the disc.
And I'm going to ask Dan to describe what happens.
It's floating. It's just in the air, so levitating.
OK, so we've actually got a magnet which is levitating about 1 inch above this disc of black superconducting material. So Ted is actually able to spin it in the air. It's spinning round. Quite remarkable. What do you think, Kathy?
Amazing.
Yeah, fantastic. So, Ted, what's happening there? Why isn't it dropping onto the superconductor?
So, just like with the aluminium, as I moved the magnet towards the superconductor, it started currents flowing around it. But these currents, chasing their tails in little whirlpools underneath the magnet, don't stop, because there's nothing to stop them if it's a superconductor, and so the magnet never falls, and it'll continue staying up there as long as we keep it cold.
OK, so the magnet which is trying to fall downwards is generating a current in that superconductor. But as we said, the superconductor, the current can't die in it. It just carries on, and so it actually manages to repel that magnet and keep it floating just above. Well, there we go. We've actually managed to levitate a magnet in a lab at Hills Road Sixth Form College. So many thanks to you, Ted, for setting that up. Any final thoughts, Kathy and Dan? How cool is that?
That is rather cool.
Yeah, excellent. Do you want one, Kathy?
Yeah.
OK, well, unfortunately, we can't hand out superconductors, so maybe another time. But anyway, thank you very much to everyone involved. And that's all from Hills Road Sixth Form College. And we'll see you next week for some more kitchen science. So goodbye.
Thank you very much, Derek. Also, Ted Forgan, Kathy and Dan for a fantastic kitchen science. Next week, we'll be showing you why fireworks come in so many different colours with the help of some chemicals and a Bunsen burner. So tune in next week to find out about that. Let's congratulate John. Hi, John.
Hello there.
I think you deserve a prize.
Well, I think I was only about half right.
Well, you were pretty close to spot on.
Yeah.
OK, well, thank you for joining us on The Naked Scientist. Don't go away. We'll get our guys to take your details, and you've won yourself a fantastic electronics kit.
Laying the facts bare, The Naked Scientists.
In a few seconds' time, we'll be talking to Alex Mishenko, who was the Science Graduate of the Year. He's also Chief Technical Officer of Ferro Energy, and he's invented a new way of cooling things down. So we'll be getting cool with Alex in just a second. But before then, over to Tim Jackson, because we have a question from Dave in Northampton, and he says he wants to know how magnets work when they're used to treat injuries, such as frozen shoulder, Tim.
Well, I'm not really sure as they do, actually. I did have some experience of this when I twisted my knee playing football, and someone told me if I taped magnets around my knee, then it would help it to heal up. The problem was that when I walked up to the window, my knee stuck to the radiator beneath it, and that didn't help my knee get any better at all.
Now, there was a trial in the... there was a study written up in the British Medical Journal, actually, few years ago now, and people looked at this question and they said, well, actually, there is evidence that people do seem to do a bit better with these bracelets and things which are magnetic, but there's absolutely no scientific reason or nor any kind of justifiable reason why people should get better. And what they suggested was that the trial was a bit biased, because how do you do this kind of trial? You give people with achy knees or achy joints or something either a magnetic bracelet or a non-magnetic bracelet. Now, it's pretty easy for people to work out whether they've got the magnetised version or the non-magnetised version. And if people are given one where they think it's a placebo, so just a dud bracelet, then they're going to claim that it works less well, we think, than if someone has a bracelet which is obviously magnetic, because it's going to stick to stuff. And so people are going to conclude, well, they want to conclude that it's actually having a beneficial effect. And then that was the basis for their argument. Now, Alex joins us. Alex, you're originally from Russia?
Yes, I'm from Russia.
Okay, what is it you've invented?
So, our team has discovered a giant electrocaloric effect in thin films. The electrocaloric effect is a change in temperature of an insulating material induced by the application of a voltage.
So what you're saying is when you apply a voltage to something, it changes temperature?
Yes, exactly.
So was this known before you came along, or is this new?
Yeah, well, the electrocaloric effect has been known for several decades, and prototypes of the electrocaloric fridges were built in Russia and the States, but they were not commercially feasible because the electrocaloric effect in known materials was not large enough.
Okay, well, just talk us through sort of step by step how it works and what you actually do.
Yeah, so you take a piece of silicon, which is about 0.5 millimeter thin and about 1 centimeter squared, and then you deposit a thin ceramic film on it, and then you deposit an electrode on top of your film, and just the application of a voltage causes the film to change its temperature. And if you build a sandwich structure, then this sandwich structure can develop a temperature difference of up to about 20 to 30 degrees C.
But it's presumably not efficient for fridges. Because I say that because presumably a fridge is already so effective that this wouldn't add much to that.
Yes, fridges are quite efficient, but they use greenhouse gases. So that greenhouse gases contribute to the global warming effect. So even if our new devices are not as efficient as fridges, people maybe still want to replace greenhouse gases in their fridges.
So, okay, assuming that doesn't happen in the near term, what else could you do using your electrocaloric effect invention?
Well, we can do air conditioners, for example. And that is more interesting because air conditioners work all the time usually. And so we can compete with conventional air conditioners in efficiency. And also, surprisingly, same kind of materials can be used to convert low-grade waste heat into electrical energy. Waste heat is produced in everything, from computers, mobile phones, and indeed in almost all electrical or mechanical devices.
So how did you actually come to discover this in the first place? Because you won Science Graduate of the Year. That's pretty prestigious. What actually is that, and how did you come to be doing this work?
The Science Graduate of the Year is an award by Royal Institution of Great Britain and L'Oreal. So that's quite prestigious, and I'm very happy that I won that prize.
What did you actually win for winning it?
I'm a life member of the Royal Institution now, and I give a lecture in London and in the Royal Institution, and I'll give a lecture in Paris, and they also gave me some cash.
Which is always nice. Yeah. Alex Mashenko, thank you very much.
Thank you.
Now, I've got a question here from Jen, who says, I'm a plant molecular biologist in the US. Thank you for keeping me company during many long hours doing experiments in the darkroom. I love your show. My question is, I don't know if you can help with this, Helen. Why does the sweat of some people's underarms turn their shirts yellow?
Something I've certainly noticed, but I don't know if I have an answer to the question. Is it something to do with the bacteria associated with your sweat that's
you'd have thought so, wouldn't you?
Causing all those nasty smells? Because isn't it also, if it's yellowier, I'm sure it stays a bit stinkier as well, doesn't it?
Well, I was thinking about this, and you're right, that obviously our armpits are a seething mass of bacteria, and those bacteria are growing on the sweat we produce, and the fact that we're squirting out a couple of litres of sweat every day all over our body, obviously. Also, they're growing on dead skin. And so there's lots of food around for the bacteria to eat. And when they go about their metabolism, some of the things that they produce are quite acidic. And so when they produce an acid, a lot of the dyes in clothing are fixed in place by various acid or alkali processes. And I'm just thinking that perhaps the acid which is produced in the armpit is sufficient to affect some of those dyes.
Could be. I have a very strange email here, a very nice one as well, though, from Julia in the United States. Thanks ever so much for your email. But sticking along the kind of electricity lines we've been talking about today, she says, if you plug a pickle into an electricity source, it will cook and light up. I also know you can do this with a hot dog, but will it work for a lemon? I have no idea. Anyone in the studio got any idea what she's talking about?
Have you tried plugging a pickle into the electrical supply at all, Tim?
No, I think there has been some research into whether or not you can cook food by passing a current through it, and I think that's where this story of the hot dog comes from.
Does it actually work, though? But theoretically it would, wouldn't it?
Well, it will get hot because of the resistance, as we talked about earlier. That's right.
OK, well, you have been listening to The Naked Scientists. Helen, who has won our competition, first of all?
Thank you to everyone who rang in. We were inundated with right answers. It was clearly something you all knew very well. The question was, what element are diamonds made out of? And the answer is, of course, carbon. And thank you very much. We have picked out of the hat Marianne in Wyndham. You will be receiving, I believe, a signed copy of Chris's book. Is that right, Chris?
Yes, I will give away a special copy of Naked Science, which is my book I've just launched, and I will sign it to her. So we'll send that to you in the post this week.
Fantastic. Well done, Marianne. And thanks as well to everyone who called in.
Well, that's it for this week. Next time, it's our Science Q&A show, and we'll be devoting the entire hour to answering your science questions. And the wackier, the better. So if you want to know what makes banana skins slippery, why ostriches bury their heads in the sand, or even how much water is locked away in a camel's hump, then send your questions now to chris@nakedscientist.com. In Kitchen Science, we'll also be investigating the science of fireworks with a Bunsen burner and some interesting types of salt. And we'll also be talking to Plymouth University's Roy Lowry, who blasted his way, we hope, into the Guinness Book of Records for detonating more fireworks in 30 seconds than anyone ever has before. For more science in the meantime, you might want to check out the Nature podcast, which you can find at nature.com/nature/podcast. We make that one too, and it's full of great surprises. Thank you to our guests this week, Ed Tart and Tim Jackson from Birmingham University, and Science Graduate of the Year, Alex Mashenko. Until next time, goodbye.